Hello everyone, welcome to this video series of DIgSILENT PowerFactory simulation. Today I'm going to simulate a circuit to calculate the short circuit current. As you can see in the schematic, we have a simple network consisting of a grid, 2 transformers, 3 cables and 1 overhead line. To start with, to the left we have a grid of 20 kilovolts whose short circuit current is given to be 10 kiloamperes, and I assume that the grid is 50 Hz. Now 2 bus bars are connected with 2 different transformers. Both are connected in DYN5 configuration. The details of the transformers are listed here to the left. One is the 630 kilovolt ampere transformer and the other is 400 kilovolt ampere transformer. In between the transformers and the bus bar, 400 volt bus bar, there are 2 cables, and these nodes are then connected with cable 3, and there is an overhead line bus bar here. The target is to calculate the short circuit current, 3-phase and single phase, at the specified locations F1, F2 and F3. Let's now turn to the DIgSILENT software and build the model and carry on with the calculation. So as you see, I have opened the DIgSILENT PowerFactory software. To start a new project, let's go to our target folder and take a new project. I'll name it example 1. With the default settings here. Let's close. So if you remember that we have a grid first and 2 bus bars connected with the transformers, nodes with cable 3 and 4. So let's take 2 bus bars. So this one, let's call it Q. Nominal voltage is 20 kilovolts. Kilovolts as well. Copy it. Let's call it Q. Single bus bar, let's call it Q, the grid. And this one to be 400 volt bus bar, which we can bus bar 400 volts. 0.4 kilovolt. Yes. So these 2 bus bars are then connected with 2 transformers. Now before adding the transformers, let's take a grid connected to this bus bar. So we can take it to the other side. I will enter the parameters later after constructing the topology of the schematic. Let's now take the terminals, a bus bar here to connect the transformers. Let's rotate them. Since the secondary side of the transformer is going to be connected to this terminal, this voltage level is then 400 volts. That is 0.4. I'll take a copy for the second transformer and paste it here. I also need here for the cable and overhead line. Let's take a 2-winding transformer from the component list and connect it here. The second one is connected here. Let's check the schematic again. So the transformers are then connected. So between these transformers to the bus bar of 400 volts, we need 2 cables. So let's go to the component list again and select that line type. Connect this. Again here to the bus bar. Connected. And in between this 400 volt bus bar to that terminal, we have another cable. To here, and we need another copy of that terminal for the overhead line. So let's start entering the parameters since we are done with the construction of the topology. Let's start with the grid. Now you can take a screenshot of it and see the values while I'm entering. I will now move it to my another screen and start entering the values. So external grid, I'll call it Q. Load flow, let's call it the slack or reference bus bar. Basic data, load flow, short circuits. Yeah. The apparent short circuit power is not given, but the short circuit current is given as 10 kiloamperes. So if you input this value, the power will be calculated 346 MVA automatically. In some cases, the minimum and maximum values of short circuit characteristics for a grid is given. In this case, this is not given, so I'll take the equal values for both minimum and maximum values given here. I'll click OK. Now for transformer 1, let's call it T1. And to enter the parameters of transformer, we need to select a type here. Let's take the new project type and enter the values. I will shorten the name as Trafo, 3-phase transformer. Rated power for first transformer is 630 kilovolt amperes. That means 0.63 megavolt amperes. Frequency is 50 hertz. That is correct. The voltage on the high voltage side is 20 and that of the low voltage side is 0.41. The vector group is delta yn 5. The short circuit impedance is given as 400 and copper loss is given to be 6.5 kilowatts. 6.5 kilowatts. Now this is important at this point to enter the zero sequence impedance of the transformers correctly. if you click on the arrow, you would see there are different options to enter the values. Since for our case we have the ratio of the zero sequence impedance to the positive sequence impedances, these relations are given, we can then calculate the zero sequence impedances from the given values. And these, let me show you how it is calculated. I will use the per unit system to enter the values. Now the relationship that zero sequence impedance is equal to the positive sequence impedance in terms of resistance, and in terms of a reactance, that is 95% of the positive sequence reactance. These relationships are given by the manufacturer. So if we include the correction factor of the transformer impedance and calculate the impedances, we will see that the values in terms of per unit are given as follows here: 0.01 and 0.03579. Similarly, for the second transformer, it's calculated here. So I will again input the values as I calculated it myself. So I'll select here. From here, I will select the reactance in per unit and resistance in per unit. And now I can input the values as I just showed you. First one is the reactance, which for the first transformer is 0.03579, and the the resistor is 0.01. So this much for the transformer. Is there any other information? If you have more information regarding like no load losses, you can input it here. For my case, it's not available, so I will leave the other default values as they are. And here, parallel transformer, no, it's a single operation of transformer, and rating factor is 100%. I leave it as it is. For second transformer, let's input the values. Similarly, I will name it T2. Choose a new project type. Let's shorten the name, trafo. It is 400 kilovolt amperes, that means 0.4 MVA. 50 Hertz is okay. 20 on high voltage side, 0.14 on low voltage side. Vector is then delta YN 5. Short circuit impedance UK is given same as the first one, 4%. And the copper loss PKRT is given to be 4.6 kilowatts. And if I calculate in terms of per unit, the reactance is given to be, for the second transformer, let me check in the other window, 0.0358486, so 0.01121. Okay, this much for transformer 2. Okay. Now let's enter the value of cable 1. That's cable 1. Again, I'm looking from the given parameters here. This one. You see, it's a 10 meters of cable, 2 parallel connections with 240 square millimeters. The conductor type is copper, and the positive sequence impedance is given here in terms of per kilometer, per unit length. So I will again copy or enter the values from the other screen. it is given 10 meters. That means 0.01. So it's 1, 2, 3. It's 0.01 is 10 meters. 0.01 kilometers. Parallel lines, as we said, it's 2 parallel lines. And type, we need to select, let's new project type, and then line type. Let's call it, let's put a short name for the cable as K. The voltage now is 400 volt cable on the distribution side. Let's keep this value 1 kiloamperes. It's a cable, AC cable, and the positive sequence impedances are given as 0.077 ohms per kilometer, and the reactance given is 0.079. Again, I need to discuss this topic for zero sequence impedance of the cable as well. Now, as you saw the values, the relationship between the zero sequence and positive sequence impedances are given as follows here. 2RL1 plus J3XL1. And if we calculate the values, it is given here. Now the same calculation follows for the other types of cable and overhead line. So these are the values I will now enter for each of the cable and overhead lines. The calculation procedure is given for the first cable, and the results for the cable 2, 3 and overhead line are just written directly. So the AC resistance R naught for cable 1 is 0.285 and the reactance is 0.143. Let's check if we need to enter some other parameters as well. It seems to be okay. Harmonics, nothing else. Reliability, cable sizing, maybe you can input here the cross-sectional area. It's 240 square millimeters. That's all. So here you can see the resulting values, a summary of the cable design or input parameters. You see, we considered the rated current to be 1 kiloamperes, but since we have 2 cables connected in parallel, the current capability of the cable system is now increased to 2 kiloamperes. And these are the calculated impedances by the software itself. Let's now visibility, input the values of cable 2. Let's call it cable 2. In the first window, let me input the positive sequence impedances as well. And the length is 4 meters. That means 0.004 is 4 meters. There's also 2 parallel lines. And the type I will select from the new project type and the line type. Let's use a short name for the cable K. The voltage is 0.4, 1 kiloampere, cable is okay. But now for the second cable, we have a different conductor type, which is aluminium. Okay, but before that, let me enter the values of the cable. Let me quickly check one thing for cable 1. If I entered the wrong values, 285 was for 0.143, seems to be okay. 0.079 seems to be okay. Okay, back to cable 2. Okay, the AC resistance at 20 degrees Celsius, let's take it as a 208.208. and the reactance is 0.068. 0.068, yes. And same for the zero sequence impedance. Let me copy the values. 0.8798 is the resistance value, and for inductance or the reactance it is 0.08228. As I said, this is an aluminum conductor, and cable sizing it's 185 square millimeters. And here again the summary. Close it. There are two more lines we need to specify the parameters for, and then we are ready for the simulation. So cable number 3. Are there any parallel? No, there are no parallel lines. It's a 20-meter long cable. Again, copper. Let's select the type. Okay, 0.4 cable AC. For this one it is 271 ohm per kilometer, and the reactance is 0.087. For zero sequence I calculated this value to be 0.813, and the other one is 0.388. This is copper, as I mentioned, and it is a 70 square millimeter cable. Let's close it. Close this. And the last one. Let's say it's overhead line, OHL. 50 meters long is the cable, so it's 0.05. And then parallel lines. It's not given, it's parallel, not, there are only one overhead line. And let's leave it as it is, and this is also 0.4. And now this is important to select this overhead line, and the values of positive sequence impedance. Again, I will just take over from my other screen. It's 0.3704, and the reactance value is 0.297. Similarly, for the zero sequence impedance, the resistive part is given or calculated as 0.7408, and the reactive part is calculated as 0.891 ohms per kilometers. So we're almost done here. Let me just input the cross-sectional area of the cable, which is 50, and then done. So to summarize again, we had the grid to the left, and then the two bus bars connected with the pair of transformers. We had cable 1 and cable 2, then connecting these transformers to a bus bar at 400 volts, and we had a cable 2 here between this terminal, and finally we had an overhead line. So as I mentioned before, that we need to calculate the short circuit current at position terminal 1. It's number, let me show you again. So fault position 1 is where we need to calculate the short circuit current. The second position is over the cable at bus bar here at 400 volt. And the final position is at the end of the overhead line. So it's a good idea to run the load flow analysis and to see if there is a problem with the model. So for that, you can go to the calculate load flow, AC load flow balanced, positive sequence, just run it. So if everything runs fine, to calculate the short circuit current, you just come here, right click on the bus bar or position where you want to calculate the current for, go to calculate and click on short circuit. Now this window is really important. You see there are different methods listed here. The one that I will go for is IEC 60909. You can choose other methods if you're interested in. I will take this one. Let's, for this part of the video, just calculate the three-phase maximum currents. You see, we can calculate both of them. And there are different versions of the norm. One is in 1990 for this. There were only 2 years, 2 versions given specified for this version of software. Now, since this is a low voltage side level, according to the norm or standard, we have 6% of the voltage tolerance. If you go to the advanced options tab, then you will see you can include a customer defined C factor. I will leave it as taken from the norm. And there are peak short circuit current calculation method given or described in the norm. There is method B, C1, C012. I will leave it the default one. You will know if you need to change any parameters later. But for this case, let's calculate the three-phase maximum short circuit current under this given scenario here. So here you see, here we have the values here. Let me rotate clockwise. So this shows SKS is the short circuit power at this bus bar. And then we have the three-phase maximum short circuit current, 34.62 kiloamperes. And for the chosen method for calculating the peak short circuit current, that is method C1 that I calculated, according to this method, we have 70 kiloamperes of peak short circuit current. Let's do the same for position 2, that is F2 here on this bus bar. We can right click, then calculate the short circuit current, specify what norm and positions, or year version, calculate. So here we had the three-phase short circuit current of 34 kiloamperes in steady state and a peak value of 69 kiloamperes. And finally, if we want to calculate the short circuit current, again, short circuit, execute. So here we have 6.9 kiloamperes of three-phase short circuit current and 10 kiloamperes of peak short circuit current. Now it would be also interesting to show the results in instantaneous waveforms. What we saw is just steady state or RMS values. But these we can discuss in the next video, since it's already getting longer. Thank you for watching, and let me know if you have questions regarding this tutorial or what else you want to learn. Thank you.